Effect of synthesis route on photocatalytic properties of 10% Ti-doped BiFeO3 nanoparticles. Abstract BiFeO3, BFO, is drawing significant attention due to its growing potential as a multiferroic ceramic and applicability as photocatalyst. Our previous research showed that Ti doping with BFO results in an increased ability of the sample for photocatalytic H2 fuel generation. This article is aimed at studying the photocatalytic properties of 10% Ti-doped BiFeO3 ceramic and investigate the effect of synthesis route on the properties. Conventional sol-gel technique were followed in this experiment to prepare Bife 0.9 Ti 0.103, BFTO, nanoparticles, which is a bottom-up synthesis process. 2-methoxyethanol were used as solvent, and to prevent agglomeration, citric acid was used as a capping agent. The energy dispersion spectroscopy, EDS, analysis confirmed the homogeneous substitution of Ti in BiFeO3 nanoparticles. From the X-ray diffractometer, XRD, patterns, structural modifications were investigated and compared. FESM results showed that finer grade particles were synthesized from sol-gel method. The bandgap energy of the selected samples was estimated from their diffused reflectance spectra, DRS, graphs by applying Kuebel-Comonc, Km, function. The absorption spectra confirmed that the prepared sample can absorb light with wavelength from UV to visible region. It also exhibited higher bandgap energy compared to the samples prepared from other top-down process. Keywords: multiferroic, photocatalysis, perovskite, bismuth ferrite, titanium doping, XRD, UV-vis spectroscopy. Introduction. In spite of having some inherited drawbacks, like wide bandgap, instability, photocorrosion, and the photo-generated charge carrier recombination etc., photoelectrocatalysts have recently obtained notable attentions worldwide. TO2, WO3, Fe2O3, BiVO4 etc. photoelectrocatalysts are recently being investigated. 1, 2. Among the numerous classes of materials, perovskites-based photocatalysts have distinct photophysical properties and offer unique advantages. Perovskites have the general formula as AbO3, where the A site and B site is occupied by the larger cation and the smaller cation, respectively. The perovskite has octahedral crystal structure where the 8 corners are occupied by Bo6 atoms. 12 oxygen-coordinated acations are located in between the 8 Bo6 octahedra 3, 4. However, the phenomena of tilting of the octahedra occurs depending on the electromagnetic properties of the A and B cations and their ionic radii. This tilting might result in lower symmetry structures and varied electronic and optical properties. Different properties like the band structure, electron and hole transportation, photoluminescence, and dielectric behavior 3, 2, 4 is affected by the degree of tilting. In photocatalysis, there are several reasons for the perovskite structures being significantly advantageous while comparing with the corresponding binary oxides. Firstly, perovskites have the potentiality to offer favorable band edge potentials allowing various photo-induced reactions. Secondly, A and B site cations can be engineered in the lattice allowing a wide scope to modify the band structure and other photophysical properties. 4. Thirdly, combining the effects of ferroelectricity with the photocatalytic effect gives rise to the photocatalytic activity, which is possible in perovskites. The enhancement of electron-hole separation and photocatalytic activity can be triggered utilizing the ferroelectric properties of BFO. Although the ferroelectric properties of BFO has been studied, its other properties like moderate bandgap, 2.2 eV, appropriate band edge positions, stability, and non-toxicity indicate its suitability as a photoelectrocatalyst for water oxidation. BiFeO3 is, however, difficult to put in application due to its having low resistivity and the synthesis process of the pure phase being intrinsic and difficult one. Some improvements in the methodology of synthesis has been studied to reduce formation of impurity phases 5, 6, 3. Recent researches are targeting to modify the magnetic, electric, and optical properties of BFO by doping it with different transition metal ions, paramagnetic rare earth metal ions or non-magnetic alkaline earth metal ions. Bi3+ ion of BFO when substituted with rare earth elements, such as La3+, Nd3+, or Sm3+, results in remarkable improvement of the ferroelectric and ferromagnetic properties 6, 2, 4, 7. Previous investigation demonstrate that GD-doped BiFeO3 shows enhanced photocatalytic degradation for rhodamine B, RHB, 8. It is also shown that Ca-doped BFO improves the photocatalytic degradation of Congo red dye 9. Yan Nanfeng and Huanchun Wang et al. Also found a similar results from their studies 10. Ben Wang et al. Showed that, small amount of senior 2+ doping to BFO can create phase transition from the rhombohedral distorted perovskite to the cubic structure. Substitution of heterovalent senior 2+ ions in BFO nanoparticles leads to better ferromagnetic property 11. However, not much studies were done on the effect of transitional metal ions such as Ti doping on BFO. Again, there are very few works on methodological comparison to establish an effective route to fabricate pure phase nanoparticles with improved properties. The selection of Ti as a dopant ion is based on the facts that the ionic radius of Ti, 0.6058 degree, is quite similar with that of Fe ion, 0.6458 degree, which is conducive to the replacement 12. Ti plus is highly aliovalent compared to the other cations Bi and Fe and 12. Ti atoms have partially filled 3d orbitals which can improve the position of the valence band 13, Vb, and change the band gap structures of semiconductors. Intriguing properties are reported for other titanium-doped nanomaterial 12, 13. A promising way of enhancing the multiferroic properties of BiFeO3 is to prepare the nanoparticles with particle sizes smaller than 62 nanometers, which is actually the size of the spiral modulated spin structure of BiFeO3 13. Notably, synthesis of BiFeO3 multiferroic nanoparticles with improved ferromagnetic, ferroelectric, and photocatalytic properties with a particle size of the order of or smaller than 62 nanometers is still a challenge to the research community. Recently, a physical technique was developed in Nanotechnology Research Laboratory, Department of Physics, BUET, to produce high-quality BiFeO3 nanoparticles directly from their bulk powder materials using ultrasonic energy 8. In the present investigation, nanoparticles of BFTO were fabricated following the conventional Sol-Gel methodology to observe the suitability of these two comparable routes. The structural, morphological, and optical properties were investigated for both bulk polycrystalline materials and their corresponding nanoparticles. Investigation of the surface morphology and the crystal structure of the samples were done by using field emission scanning electron microscope, FESM, and X-ray diffraction, XRD, techniques, respectively. Optical properties such as absorbance, reflectance and band gap energy were investigated using UV-Vis spectrometer. 2. Methodology. A. Sample preparation. The calculated amounts of Bi, NO3, 3.5 H2O and Fe, NO3, 3.9 H2O were taken in 2 beakers separately. To dissolve these, 70 ml of 2-methoxyethanol, each, was used as the solvent. In another beaker, 50 ml of 2-methoxyethanol was poured, and Ti-butoxide was introduced in it with the help of a pipette according to the calculation. Here to mention that Ti-butoxide reacts readily with the moisture in air, and forms a solid. To avoid this, the process needs to be fast. Citric acid was also dissolved in 2-methoxyethanol. It acts as a capping agent. Sol-Gel being a bottom-up process, the particles grow larger from atomic scale. When these are small enough, their surface energy is much higher. To reach an equilibrium of energy, the particles tend to agglomerate on the surface. This may reduce the photocatalytic properties of the particles. Citric acid hinders this process. 3 separate solutions were then mixed together to form the sol and stirred by a magnetic stirrer. The temperature of the solution was kept at 100°-110° C to evaporate. The temperature of the solution was not allowed to rise above 110 degrees Celsius, as 2-methoxyethanol boils at 120 degrees C. After 8h of continuous stirring, the solution gained a gel structure. The gel was then dried to powders, taken in a crucible for drying, and put in the oven. The temperature was set to 80 degrees Celsius for 24 hours. To get the nanoparticles the material was calcined at 650 degrees Celsius for 1 hour. Ramping rate of the furnace was 20 degrees C/min. The nominal composition of biphase 0.9 Ti 0.103, BFTO, bulk polycrystalline materials were also synthesized by a conventional solid-state reaction technique, and by using ultrasonication technique corresponding nanoparticles were produced directly from their bulk powder materials. Characterization. To observe the crystal structure of the bulk, the pellets were ground into fine powders while the nanoparticles needed no additional measure. The structural properties and phases present in the crystalline samples were determined from the XRD patterns given by the X-ray diffractometer, Bruker D8, Cu Ca1 radiation. Equals 1.540598 A, in the range 2. Equals 20°-80 degree. To study the surface morphology and chemical homogeneity of the samples, field emission scanning electron microscope with energy dispersive X-ray spectroscopy, EDS, FESM, model, JEOL-JSM 7600F, was used. The UV visible absorbance spectra of the samples, range, 200 to 800 nm, were recorded using a UV spectrophotometer, UV 2600, Shimadzu, where BASO4 was used as the reference material. 3. Result and discussion. A. Structural analysis. Successful TI doping has been confirmed by EDS elemental analysis. EDS, energy dispersive X-ray spectroscopy, analysis were done for 3 different positions of ThEP-Repard sample, and it is confirmed that O, Ti, Fe and Beelements are homogeneously present throughout the prepared BFTO ceramic nanoparticle. As seen from EDS result, Table 1, the actual TI doping contents in the BFTO bulk sample was detected to be 3.37%, which is very close to the theoretical value. From the EDS spectra, it is observed that carbon content in the sample is very small. Calcination process in air removed almost all of the organic components off the gel, which eventually resulted in low carbon content. From Figure 1, a common peak for platinum can be observed in the EDS spectra, which can be attributed to the platinum coating of the particles prior to performing the spectroscopic analysis. The structural properties of biphase 0.9 Ti 0.103 ceramics and their corresponding nanoparticles were analyzed with powder X-ray diffraction, XRD, method. TI doping reduces the presence of secondary phases, as has been evidenced in our previous work 14. Main reason behind the impurities are oxygen vacancies, volatility of bismuth and transition of Fe2+ to Fe3+. However, the mechanism leading to the formation of those secondary phases is still unknown. The size of the particle can also be assumed from Fig 2. Scherer equation helps to understand this. 1. Where T equals mean size of the ordered, crystalline, domains, which may be smaller or equal to the grain size, equals a dimensionless shape factor, with a value close to unity, equals X-ray wavelength, equals Bragg angle. Point 2. Equals line broadening at half the maximum intensity. So an increase in point 2 will decrease T, so the size of the particles decreases. The nanoparticles obtained from Sol-Gel method shows better structure than the ultrasonication nanoparticles, or the bulk, solid-state, particles are smaller with less irregularities. Also, the splitting peaks are tending to merge more smoothly in the Sol-Gel sample. The smaller particle size of Sol-Gel sample is also confirmed from FESM, field emission scanning electron microscope, images. From the histogram, Figure 3b, it is evident that the grain size distribution is pretty homogeneous and the average grain size of nanoparticles has reduced to 70 nanometers. While we observed in our previous work that the average grain size for BFTO nanoparticles prepared from ultrasonication method was 90 nanometers 14. It has been previously observed that Ti doping increases the porosity in surface morphology of BFTO nanoparticles. Fig 3 also confirms porosity which might be attributed to the higher oxygen vacancies of the sample. Optical properties. The absorbance spectra of the selected samples were investigated with an aim to probing their optical properties. 10% Ti-doped nanoparticles prepared by Sol-Gel technique shows absorption edges at 640 nanometers, which is, although less than that for undoped bulk BFO material, higher than any other BFTO bulk and nanoparticles prepared by solid-state route and ultrasonication method. 14. This evidently indicates blue shift from its bulk sample. The blue shift may be due to the bandgap energy modification due to ultrafine nano-sized particles. However, the absorption edge value shows that tested sample can absorb light with wavelength from UV to visible range. The diffuse reflectance spectra, DRS, were performed to investigate the major transitions and to estimate the bandgap energy of the synthesized selected sample. The direct bandgap energies of the samples were estimated from their DRS graphs by applying Kubel-Communk function for direct transition, where f, r, is defined as. Our previous work showed that, Ti doping caused to reduce bandgap energy from 2.45 eV and 2.58 eV to 2.28 and 2.29 respectively for BFTO bulk and BFTO nanoparticle samples prepared by ultrasonication. The BFTO nanoparticles prepared by Sol-Gel method shows even smaller bandgap energy, which is 2.16 eV in magnitude. This decrease in bandgap energy may have happened due to the ultra-reduced size of nanoparticles as observed from the SEM patterns. The reduction in size may have affected the crystal structure. 15. Structural distortions essentially alter the bond angle in the system. In this perspective, the bandgap increment found in the case of 10% Ti-doped BFO nanoparticles prepared by Sol-Gel method could be attributed to the lattice distortion owing to the alteration in the rotation of Fe6 octahedra in the unit cells. Such modifications might also influence the band edge positions that lead to an increase or decrease in the bandgap energy of the synthesized materials. 10. A lower bandgap energy indicates higher charge separation, hence accelerate photocatalysis. 4. Conclusion. 10% Ti-doped BFO nanoparticles were prepared using conventional Sol-Gel method. Comparative investigation on structural, morphological, and optical properties were performed between the sample and other BFTO bulk and nanoparticles prepared from solid-state and ultrasonication methods respectively. Sol-Gel method produces finer grade nanoparticles which contributes to blue shift of bandgap energy of the sample. Synthesized BFTO samples absorb UV ray from visible range. It also exhibits generation of less impurity phases. Due to check in formation of oxygen vacancy, Ti doping in BFO by Sol-Gel method is presented as more effective synthesis route. All the properties indicate its high potentiality as photocatalysis for solar H2 fuel generation. Acknowledgement. This research was performed in Nanotechnology Research Laboratory, Department of Physics, BUET, Dhaka. XRD and SEM investigations were done in Department of Glass and Ceramic Engineering, BUET.